Hi everyone, Professor Muhammad Sharaf with you. Our subject today is to give a literature about solar still. We have to return back to solar still. We can manage single slope solar still, but by the aid of waste heat from biogas stove cooker. First of all, remember that you have to log to your model after you download your model. You have to assign your specific folder, which drive, which folder. Go from here. Don't open your model from inside folder. You have to open it from here, okay, in order to show all the features. So your model should be appear from here. Double clicking here, okay. Okay, our model should appear like this. As you can see, you have to check model browser, show model browser, all of these and all of this. Okay. What is our model today? What is our main components? Okay, our components are it's a storage tank or feed tank. Let it be a brine feed tank, and we have some kind of heat exchanging between a stove cooker. This is stove cooker for cooking, and it's for it's supposed to be utilize biogases. Okay. In order for cooking, and we can make some kind of water jacket in order to transfer heat from the stove cooker in order to reheat the brine going to the solar still. This is single slope solar still, and it's supposed to work as double acting unit. It's supposed to working as solar distiller and a condenser and during sunset periods. Therefore, during sunset, during the absence of the sun, we can use this cooker in order to increase the temperature of the brine and making some evaporation and condensation. But I don't recommend such things because it's solar still what is one of its favorite operational features, that it has to be utilized by only solar radiation. Okay. So you can double clicking here for more information. You can log into our YouTube channel. Okay. Clicking here, you'll find out your model. This is your model environment. You have storage tank, stove cooker, and solar still design model. Okay. You have to assign some inputs. Let's begin from tank. We have to assign operational hours of your tank. What is your operation hour? Suppose it should be around for 8 hours, okay, or 24 hours, whatever. Okay. What is your inside tank temperature? Normally it's around ambient temperature, so I will keep it at 25 as a reference temperature, and salinity of the feed. For such technique, I think your salinity is from 400, because this is the range of salinity which is harmful to the human body. So from 400, 500, something like this, up to 45,000 ppm. So I suppose it's around let it be 2000 ppm as a brackish water. What is your tank diameter? It's up to your design. I'm not sure about it. Maybe 1 meter. Okay. Flow. What is your pipe feed pipe diameter? in inch, 1 inch, 1.5 inch, it's up to you. Suppose it's 1 inch. And tank head, suppose it's 3 meters. Okay, let's hit apply. We can ignore minor losses and major losses because it's a simple technique. Okay, for stove cooking, we have here, what is your reference temperature? I will unify our reference temperatures through the whole cycle. It should be 25 ambient temperature. And the stove bulking temperature, you can use dynamic modeling while changing your operating conditions. The stove bulk temperature, I think, let it be, I was stuck at 350 degrees Celsius. You can change this if you would like. Just click here, right clicking, and go to mask and edit mask or mask parameters. Let it be mask parameters. Okay, oh, I'm sorry, edit mask or Control M. You have to go to this parameters and dialogues and going to stove bulk temperature. Let's emphasize here stove bulk temperature, and you can increase your range. You can control your range from here. Okay, you can control the upper and lower limits for and the same for each unit. You can control something like this. Okay, what is your calorific value? Suppose it's a natural gas, 4,000 kilojoule per kilogram, 40,000 kilojoule per kilogram, 50,000. You can Google this. Or okay, inner diameter, as you can see here from the photo, we have inner diameter of the stove and outer water jacket diameters. So you can assign, suppose it's 0.5, for example, the inner diameter, and the water jacket diameter, it's around 0.6. The stove efficiency, I think it's around 80, 85, something like this. Hit apply. Okay, let's go for solar still. This is our main target today. You have to go double clicking and trying to discover what we can do about that. Okay, solar still productivity. Suppose you are going to use it for 5 persons, a small family, 5 persons. Therefore, suppose we need, each person needs around 5 liters per day. So suppose it's around from 25 up to 35 kilogram per day for a small family. Okay, ambient temperature around 25, and daily average solar radiation, it's about your related to your location. Okay, it's related to your location. I was stuck with 15. Okay, basin temperature, what is your temperature here inside, the temperature of the brine? Suppose I'm going to use the stove. I think it's around 50, 55, 60 degrees Celsius. I think this is quite normal. You can address the effect of this. Average wind speed, you can actually, what is your average wind speed in your local area? Area ratio between the glass cover and the basin. Okay. Okay, so I think it's around 1 for single slope. It's around 1 for single slope, or 1.5, maybe 1.5. Okay, or 1.2. It's up to you. Okay, and I think it's 1.5. Okay, operating hours, the same operating hours. Okay, these are the cost parameters. Plant lifetime, concrete construction, if you made this from concrete or from wood, it's up to you. Glass cover costs, land costs, etc. It's up to your location and your space. Okay, that's it. This for larger analysis of solar distillation, solar steel plant. If you managed to work for more than 1 meter cube per day, or you can change the productivity of of the day, or the accumulation of your system productivity. Save. Let's hit run. It's simple, 3 units. Let's hit run and see. At 0 time, you have to check this for 0 time. Okay, it's finished. Let's go and discover unit by unit. Okay, first one is the feed tank. So water level inside the tank. This is water level inside the tank, and this is total height. Okay, this is a pressure, feed pressure going to the solar cell in kilopascal, and this is tank volume. And I think it's a small tank, therefore we have to. There's no need for 1 meter. It's around, I think it's 0.5 meter as a tank diameter. Okay, small tank, and I hit run again. Okay, this is flow velocity meter per second, cross sectional area of your tank. Okay, and for stove, this is brine flow thermal power, because it's a small power because of small quantity of distillate, and this is thermal power of the stove. Okay, and this is the thermal power transferred to the brine flow. Okay, and this is biogas mass flow rate. So you have to consume around 0.14 kilogram of gases per hour. Okay, and this is overall heat transfer coefficient, stove length. This is your stove length. Okay, and don't forget to check double clicking here or highlight here your signals, and send signals to the data inspector here. Okay, in order to discover the effect dynamically. For solar cell, let's go here. This is our model, and see our solar cell efficiency. It should be around 47%, and solar cell area we are going to use around 35 liter per day. We are going to use around 12 square meter. And for glass cover, this is the area of the glass cover, and this is the depth, brine depth inside the solar cell, and this is tilted angle. It's around 24. Insulation thickness in centimeter. This is productivity per kilogram per square meter per day. Okay, and this productivity was black dice. If you added the black dice, glass cover temperature, it's around 36. Evaporation energy, this is radiation energy, and radiation from the glass cover energy. Overall, this is convection heat transfer coefficient inside your solar cell, evaporation exergy, and total exergy analysis. Okay, and this is your cost analysis. Okay, this is your cost analysis per liter. Okay, it's quite simple, direct, and an easy one. So suppose I am going to let's go and trying to work dynamically. So I have to check this by infinity. Okay, and saving this one, and I'm going to try to, I hope to try changing my productivity. Suppose I will begin from 1 meter, 1 liter per day. Okay, 1 liter per day, and try to make some changes and see the effect on our operating conditions and design parameters. Let's hit run and see what we can do. Let's hit run. Okay, let's increasing. I would like to increase the productivity up to upper values. Okay, let's go up to for example 400 or 500 liter per day. It's a plant. Okay, 500 liter per day, and as you can see here, 40, 42, 40, okay, 500, okay, and hit okay, and stop, and let's go inside and see our results. Okay, this is our results. It's a third run. Okay, let's discover water level inside the tank. This is your water level inside the tank because you increased the productivity rate, so you need a larger tank and so on. This is your okay, and this is your total height. This is your total height. It's around 5.5 meter, so your tank should be not less than 3 meters in height. I think we can put it here because they are in meters. Okay, this is the total, and this is the water level inside the tank, and this is your tank pressure. Okay, so it's increased, and tank volume, meter cube, and this is your flow velocity increasing because you increase the system productivity, and this model can be used for a plant construction. Suppose you need larger project for solar steel, not for a small amount of fresh water. Okay, let's go here, and this is tank cross-sectional area. It's constant, no doubt, and brine. For thermal energy is just brine energy, stove thermal energy. Okay, as you can see, there is a difference between flow energy and the stove energy. Stove energy is larger because the efficiency of the stove. And biogas mass flow rate. Okay, this is biogas mass flow rate in kilogram per second. And we have overall heat transfer coefficients remaining constant. Stove length. Okay, stove length is increased because the increasing of requested heat. Okay, capital. Let's go for solar steel area. Yes, thermal energy, radiation, glass cover, heat transfer coefficient. Okay, and this is your exergetic analysis. Exergy, total exergetic, and glass cover area. Let's go for, you can add more figures from here. We can add more figures from here. Okay, because so many parameters. Okay, you have to wait for a while, and let's go here, and this is a brine depth in centimeters. Remaining constant. Okay, and the productivity per day. Okay, and this is let's go for energy. I'm sorry, thermal energy was just yes, from here I have to okay, so this is our results based on the changing of system productivity. And surely you can send your figure, you can send your all of these figures in order to control them by the use of MATLAB plots or editors, so you can control the lines and everything. Okay, I have to wait because there are so many figures. I have to close this one. Okay, let's head back here. I'm sorry, I have to wait. Okay, this is our figures. I'm sorry about that. Okay, go to plot editing, and you can edit your plotting, or send your data to you can control all of your outputs and so on. Okay. I'm trying to let's go and trying to inspect the changing of another parameter. Let's go for solar radiation. I will begin from 8 megajoule per square meter. Okay, and I'm trying to change. Let's hit run again and see the effect of solar radiation. And you can use surely signal builder and whatever you would like. I'm sorry. Yes. Let's see change. Increasing solar radiation, as you can see here, up to 15 megajoule per square meters. I'm going to 15, quite normal 15, and let's go for 15. Okay, that's enough for this. Okay, 17. Okay, patient temperature, let's increase patient temperature up to 65 and see, or 70. Okay, let's hit stop and see our results. Click here, data inspector, and you can compare results. These are the results of run number 3, and we have here run number 4. So you can add and discover water level inside the tank. Is it changed? Yes, there is some changes. Okay, and total height changing, and let's go for brine flow and power. Okay, and thermal, as you can see here. Let's go for another. This is our productivity here. From here, that's productivity, and let's see. Yes, I think it's this one. Okay, and brine depths, you can seek it from here. Brine depths in centimeter. Okay, this is your brine depths changing because of the changes in solar radiation. Solar still area, let's see our solar still area. Yes, solar still area, as you can see here, decrease because you increase the solar gain by the solar still from the sun. So it's as you can see, this is your results, and radiation effect, and from glass cover to the ambient. Okay, and convection, heat loss, and this is stove length. I think stove length. I think there is no changes in the stove and tanks. All changes have been made on the solar still. Okay, so we have here single slope solar still, so you can control and manage based on your operating hours, based on your operating conditions. What is your favorite design? Okay, what is your total system productivity? So you can control what you would like, and we can manage out your results. Finally, I would like to thank you very much for your interest in our model. Don't forget to like, share, and subscribe to our channel on YouTube. Thank you very much.